So now I'm going to introduce something a little different. I'm going to put a resistor between the battery and the capacitor. So what happens now is that when I close the circuit, it's harder for that current to flow through the resistor, and as a consequence of that, the current builds up, but it takes time. And that can be shown here when I close the switch. Look, it took time for the capacitor to develop charge across it because it first had to squeeze through that resistor. And of course, the larger the resistor, the longer it's going to take to charge because the harder it is for the current to squeeze through. And watch what happens. Now it takes a long time. And that's what it would be like without a resistor. Now the reason I introduced this is because a resistive capacitive circuit, as this is called, is a far more realistic situation that exists in an axon than just a wire going directly to a capacitor plate. And the reason is this. Right? Here I have an axon, and on the left-hand side I have an electrode that's going to inject current into the axon, and then I have another electrode in the axon that's going to record the membrane potential. So now what I'm going to do is I'm going to inject some current, and the current is going to go and change the charge across the capacitor. That is, it's going to change the membrane potential. But it's going to take time to change the membrane potential, as shown on the right. And the reason it takes time is because the internal resistance of the axoplasm retards the flow of current down the axon. It acts just like the resistor in this resistive capacitative circuit. Hence, the membrane has what's called a time constant. That is, it takes time for the membrane to change its charge. That is, it takes time for the membrane potential to change when current flows down the axon. So now we're going to direct our attention to the membrane resistance. And remember, the membrane resistance simply is determined by the number of open ion channels that run through the membrane. So, before we can discuss that, I have to introduce a few new terms and concepts to you. They're not difficult. They might sound it, but they're not. The first is Ohm's law, which says that voltage is equal to current flowing through any circuit times the resistance of that circuit. Some of you may be familiar with it. I know some of you aren't. It's not hard. Follow the logic. If we transpose terms, and because conductance is equal to 1 over resistance, the current flowing through the circuit will equal the voltage times the conductance. And all that's saying is the higher, the easier it is to flow, and the more voltage you have, the more current you get. But we're dealing here with ions flowing through ion-selective channels. Therefore, voltage is actually a little bit different. It's called a driving force. And the driving force is equal to the membrane potential minus the equilibrium potential. So the current flowing through an ion channel is equal to the driving force times the conductance. The driving force is exactly what I've been saying in words all along, although I haven't mentioned that specific term. All it says is, if the membrane potential is different from the equilibrium potential for that ion, the ion is going to flow. That's all it's saying. And the greater the difference between the two, the greater the drive on that ion. Let's just use a few examples just to make this clearer, all right? So, let's take one example. For potassium, at the resting potential, the driving force will be, the resting potential is minus 70 millivolts minus the equilibrium potential, which is minus 75 millivolts. Therefore, the driving force is plus 5 millivolts. And all that says in words is that you have a high concentration force driving potassium out of the cell. But however, the cell is very negative on the inside, which is holding the positive potassium charges inside. However, the concentration force is just slightly greater than the electrical force, and that difference is plus 5 millivolts. Thus, the concentration force tends to drive a little bit of potassium out, the driving force being plus 5 millivolts. That's all it says. Now, we can take for potassium at a membrane potential of 0 millivolts. The driving force will be much higher. In fact, it will be 0 millivolts minus 75, which would be plus 75 millivolts. And all this is saying is that there's a large driving force because there's a large concentration force driving potassium out of the cell, but there's no negativity holding it into the cell. Thus, there's a large force driving it out, and that force can be given a number, plus 75 millivolts. For sodium at the resting potential, the driving force will be minus 70 millivolts minus plus 55 millivolts, which is minus 125 millivolts. There is a huge driving force, and the driving force is huge because the concentration force driving sodium into the cell is large because sodium is concentrated on the outside. And second of all, it's attracted into the cell by the electrical force because the cell is negative on the inside. The two forces are working in exactly the same direction. Thus, the driving force is huge. The number is 125 millivolts. The only thing the sign means is the direction of the flow of the ion. If it's negative, the flow will be into the cell. If it's positive, the flow will be out of the cell. It's that simple. It's not more difficult than that. Okay, let's take a few examples and see what happens. So let's take an example for sodium. And here, let's say the conductance is high. Let's say all the channels are open and the driving force is large. And it's large because the membrane potential on the inside is at rest. It's minus 70. So the driving force is going to be minus 125 millivolts. And what that means is you're going to get a lot of sodium coming into the cell driven through the channel. Now, remember Ohm's law. The current is equal to the driving force times the conductance. Now let's double the conductance. And all that means is I have twice as many channels that are open. I just double the number. And what that means, I get twice the amount of current, twice the number of positive charges of sodium carried into the cell because there are two channels open. That's all it means. Now, we can reduce the driving force by making the inside of the cell minus 10 millivolts. Now the driving force is only minus 65 millivolts. You can see it up here. Minus 10, which is the membrane potential, minus the equilibrium potential, which is plus 55. So minus 10 minus 55 is minus 65 millivolts. The driving force is lower than it was when the inside of the cell was minus 70. So sodium is going to be driven into the cell, but less of it. I just show that a little slower and smaller number. And if I double the conductance, I get, again, double the amount of current through the two channels that I would get through the one channel. Hence, if I double the conductance, I double the current for a particular driving force. Now, let's say the conductance is 0. Right? Then the current is equal to minus 125 because the inside of the cell is still at rest, but the conductance is 0. If the conductance is 0, no sodium can come in, there can be no current. And the same thing happens even if we double the conductance. Both of them are closed. 0 times anything is 0. And now, let's leave the conductance high, but make the driving force 0. And we make the driving force 0 by making the membrane potential set at the sodium equilibrium potential, plus 55 millivolts. So the driving force will be plus 55 millivolts, which is the inside of the cell, minus plus 55 millivolts, which is the equilibrium potential for potassium. So the driving force is 0. So the current has to be 0 because the driving force is 0 times the conductance is 0. One in, one out. One in, one out. That's what at the equilibrium potential. That's what it means. For everyone driven in by its concentration force, one will be repelled out by its electrical force. There will be no net flow of sodium. And I can double the conductance. It makes no difference. The driving force is still 0. There will be 2 in and 2 out, one through each channel. but there will be no net flow of current. That's all it means. So the current equal the driving force then the conductance. And if the driving force is zero or the conductance is zero, there will be no current flowing across the membrane. So finally, we're going to be considering our internal. That is, the internal resistance of the axon, which is really the simplest because it's only determined by the diameter of the axon. The larger the diameter, the lower the resistance, that is, the higher the conductance, and the smaller the diameter of the axon, the higher the resistance. And let's illustrate that here. Say I have an axon. This is a large axon, and I've injected a lot of positive current into the left side of the axon, and the left side is now positive, and I want to see what kind of current is going to flow from point 1 to point 2. Point 2 is still very negative, the normal resting potential of the cell. So by Ohm's law, the current that flows down this axon should be equal to the voltage divided by the resistance of the axon, or the voltage times the conductance, whichever you want to look at it. But the internal resistance of a large diameter axon is small, so that a large amounts of current will spread down the axon, as shown here, simply by Ohm's law. You can look at it a little differently if you want to. You can say that the current will be equal to the voltage, which is constant here, the voltage difference between point 1 and point 2, times the conductance, and the conductance is very high, so you'll get a large amount of current. Simple enough. So now let's ask the same question of the small diameter axon, the one shown in the lower part of the figure. And notice the internal resistance of the small axon is large, that is, the conductance is low. So only a small amounts of current spread down the axon. So imagine we have 2 points, 1 and 2, with exactly the same potential difference that occurred in the axon on top, the larger axon on top. But now, because the internal resistance is so high, you would only get a small amount of current spreading down the axon. It wouldn't spread nearly as far as it did in the large axon. So it's the diameter of the axon which basically determines the spread of current down the axon because of the difference in the internal resistance. And in the next movie, we're going to see how these features, particularly the diameter of the axon, can regulate the conduction velocity of the action potential.